All right, let's begin. Welcome, everybody. So before I introduce today's speaker, let me remind everybody that all the video recordings of the previous talks of the semester are available at the New York Group Series Seminar webpage. Also, we are planning a one-day workshop, the Manhattan Algebra Day, at the end of the semester. So it will be on Friday, December 4th, and a preliminary schedule is available also at the New York Group Series Seminar webpage. So you can look it up there, and there will be an announcement about that sent later. So once Annalisa, our today's speaker, starts speaking, I want to remind you, please put yourself on mute. So when you want to ask a question, please unmute yourself and ask a question. So that's our standard protocol. After the talk is over, and when the recording stops, you don't have to disappear right away. As usual, we'll have an extended period of informal discussion and conversation for those who want to stick around. And with that said, I'm pleased to introduce today's speaker. It's Annalisa Massaccesi from University of Padova, and she's going to tell us something about currents with coefficients in groups and applications to network optimization problems.
Okay, thank you very much, and good afternoon to everybody. First of all, let me thank Professor Kapovic for this very kind invitation, and let me do an a priori apology, because this is my second webinar in the whole career, actually third one if one counts the popularization. So I hope, I'm not completely at ease with all these technologies, and I hope to keep it as fluid as I wish, but I know I won't. So the topic of my seminar is currents with coefficients in groups and application to networks optimization problems. It's a joint work mainly with Andrea Marchese from the University of Trento and other collaborators that I will mention. And well, it's a series of papers that actually started with my PhD thesis. So, despite the fact that the order in the title is currents with coefficients in groups and then applications, as you can see from the summary, I will follow the opposite order. So I'd like to start with concrete problems, with the applications I have in mind. And it should be also somehow lighter. And then we will open a big parenthesis on currents. At first, classical currents, and then we'll see how to adapt the theory and the framework for our target, for our problem. And then we'll see what happens also for a slightly different, more complicated case, which is the multi-material transport. So what about concrete problems? Let's start with a classical optimal transport. Well, if you think about the optimal transport in the formulation given, for instance, by Monge, you know that you are given two measures which are compatible, meaning that they give the ambient space the same mass, and this is just right, just a basic requirement. And you want to move the first measure, mu minus, onto mu plus in what we could call the cheapest way. And in classical optimal transport, the cost which is behind this wish of spare money is a cost which depends only on the distance between the initial point occupied by the particle and the ending point. You can, of course, imagine that these measures are like pile of sands, or and you want to build a castle or something like that. So you can really imagine you want to move particles, and the cost, I was saying, depends only on their distance. So since nobody is questioning the way you are going to move that particle from one point to the other one, it's obvious that you're going to do it in the one way you would think about along a segment, or a geodesic if you want to live in a Riemannian manifold. Okay, so if your measures are
You might have lost our speaker at the moment, right?
Yeah, I don't. Or she's muted.
Yeah.
Can you hear me?
Now we can, but
yeah,
you disappeared for a moment, and now we lost the slides. You know, so there were probably a few seconds of what you were saying that we lost.
Okay. So I'm back to the slides. Can you see them?
Yeah. Yes.
Okay. I'm very sorry. So I was speaking about optimal transport, and I was saying that so you can imagine that you're moving particles between mu minus, the initial measure, and mu plus, the target measure, and the cost of the transport depends only on the distance between these 2 points. So you're not questioning the way you will move this particle, which is along a segment joining these 2 points, or a geodesic if you are in a Riemannian manifold. So branched optimal transport does something slightly different, because this time the cost is more sophisticated and takes into account the path for the particle. In particular, usually the cost is subadditive, so it favors clustering of particles. It's like a discount you do for traveling together, for moving the particle together. And this is something very natural if you think about it literally. This is what happens for plants, for rivers, even for our own cardiovascular system, for instance, our own like animals, warm-blooded animals. So let me try to explain why this branched optimal transport, this subadditive cost is reasonable. I'll try with a picture, so I'll share now the whiteboard. You can see it, right? So imagine as a branched optimal transport to have an irrigation problem. By irrigation problem, I mean a problem where one of the 2 measures, either mu minus or mu plus, is just a multiple of a direct delta on just 1 point. Irrigation problem, because what you imagine usually is to have a well with water, and you want to bring this water to the plants you want to water. So the problem becomes to build a network in the cheapest way, in such a way that you bring enough water to each of these trees. Like say you're reasoning per water units. Here you start with 4 water units, and you have to bring one of these units for each tree, and you will build a network. Maybe you have some branching here, 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 and here. And what about the cost? Well, likely you're going to pay for some pipes to build your network, and of course the cost of the pipe depends on the quantity of material you spent to build this pipe. So it depends on the length of the pipe, of course, and then on the section. Imagine the pipe has a circular section with radius r. Well, what happens is that the cost goes like the perimeter of the section, so it goes like r. While the quantity of water, you can, the maximal quantity of water which will flow through the section of the pipe is something going like the area of the section. So it is something going like r squared. So you see, if you start from a certain amount of water that you want to allow to travel in your pipe, the cost is sort of its square root. In the example, what happens is that here you want 4 water units to travel in this segment, in this first segment. So the multiplicity, if you want, in this piece, in this chunk, is 4. But what you're going to pay is 2, the square root of 4. And in here, you have a multiplicity which is 2, and you're going to pay square root of 2. Here 1, 1, and here again, from 2 to square root of 2, 1 and 1. So that's why we say that this is a reasonable way to imagine that our cost is working.
Sorry. So what you just explained, this depends on the combinatorics of this tree. This is not yet a feature of the ambient geometry. It depends on how this tree looks like, right?
Yes, yes.
Okay.
Okay, and the other fact I want to emphasize is that you can choose also other costs. Usually what you do for branched optimal transport is to take the modulus of the coefficient theta to some power alpha, where alpha is a number between 0 and 1, and this preserves our subadditivity. And well, if you let alpha tend to 1, you recover the classical optimal transport, because you lose subadditivity and all of a sudden it's enough to irrigate with a cone construction, just sending straight segments to your trees. While if you go on the opposite direction, so you send alpha to 0, what I want to convince you is that we're going to recover a Steiner tree problem. Why? Well, because when alpha goes to 0, the cost of the pipe won't depend anymore on the perimeter of the pipe itself. The cost of the pipe is the same for every radius. So the point is whether you build something or not. Only the length of the pipe matters. So imagine you have another irrigation problem. Here there is your source, here you have your wells, and you're just computing the sum of the lengths of the segments. So let's go back to the presentation. Okay. As I was saying, we have among our concrete problems, the Steiner tree problem, even if this is not the way you would tell a friend about the Steiner tree problem. Usually what you say is that given endpoints in an ambient space, say the Euclidean space, maybe the plane R2, you want to find the shortest connected set which contains these points. Okay, and then if we want to push a little bit further our set of concrete problems, we can also treat the so-called multi-material transport problem, which is better known in the literature as multi-commodity flow. What does it mean? It means that we want to build a network that we want to exploit to transport more than one material. So maybe it's both water and oil, or I don't know. And as an example, I can show you this technology, which is called power line communication technology, and allows customers to use the electric power distribution network for data transmission. So if you want to Google it, the most recent version is called broadband over power lines. And you see from this example that electric power and data signals cannot be treated as the same thing for a couple of pretty solid reasons. The first reason is that the cost dramatically changes between the electric power and the data signal. In particular, if you want to build a network for the electric power, you have to buy some cables, and the thickness of these cables has to be chosen depending on how much electricity you want to put on the cable. And these cables are really expensive. The data signals, on the contrary, once the cable is there, it doesn't matter how thick it is, they travel almost for free. So there is really a big difference. And then the other problem is that the boundary datum is changing, because electricity and internet supply of two different things are subject to different demands. Because maybe you have solar panels, so you just need the internet cables for your house, or on the contrary, you live in a very rainy place, so you need electricity, but you're fine with having the internet only on your smartphone. Okay, so just to do a brief summary, mathematical summary of what we have seen up to now. We are given, for simplicity, say for the moment, two atomic measures, so mu minus and mu plus. And the network can be modeled in two ways, with a Eulerian formulation and a Lagrangian one. I'm going to focus on the Eulerian formulation. So the network is modeled with, say for the moment, an oriented graph with multiplicity. What does it mean? It means that we have this formal sum where we put the segments, sigma I, and a multiplicity, a coefficient before the segment, which belongs to Z when we're dealing with a branched optimal transport, or to Zm when we're dealing with multi-material transport. Because if we have more than one material, say M different kinds of materials, then we want to register each material in a different entry. So we need a label for each material. And then this graph has a boundary, which we want to match with the difference of the two given atomic measures. And what we want to minimize is a total energy. A total energy which is computed for each oriented graph in the trivial way, as the sum of the lengths of these segments times the cost evaluated at the coefficient, the multiplicity, this theta, where the cost, of course, fulfills some assumptions. It should be admissible, subadditive, but we're going to see the the assumptions on the cost later. And here there is a list of good properties that we should have in mind for our minimal networks. So the first good properties, of course, like Anselmo d'Aosta would say, the most perfect one is existence. So for the existence of a network with that boundary, that's pretty easy. We just draw a cone. We perform a cone construction and we get a network with that boundary. It's not that trivial or true that that network will have a finite cost. Indeed, what happens, for instance, for costs like power alpha of the modulus of the coefficient is that every measure can be irrigated if alpha is big enough. So if this is bigger than 1 minus 1 over d, d is the dimension of the ambient space. For instance, in the plane, this is 1/2. Alpha should be bigger than 1/2. Otherwise, you cannot irrigate measures like, say, the Lebesgue measure on some open set, because you have too many branches and your energy explodes. Okay, and then after the existence, always regularity comes. So you also want to collect some regularity infos about your minimal network. You want to know it is a locally finite graph, it has a tree structure, and the so-called single path property. So a certain list of regularity features. And then there are these two properties that I should treat together, and they have a computational flavor somehow. Because, of course, this is a concrete problem and you want to treat it also numerically. And, you know, among our problems, there is the standard tree problem, and the standard tree problem is NP. So, first of all, you would be very happy even if in some special cases you can take shortcuts instead of performing these heavy computations with a computer, with like Geo-Steiner. And the other computational issue is stability, because, okay, if your measure is discrete, as we were saying, there is some reshuffling, some combinatorics to do, but you can do it. But if your measure is diffuse, this is not something you can really tell to a computer. What you have to do is an approximation of your measures, mu minus and mu plus, and then for each pair of mu n plus, mu n minus, you compute a minimal network, say Tn, then you take the sequence of this Tn and you hope it converges somewhere, not really to any network, but to a network which minimal one between the two original initial measures.
Just a second, Annalisa. So you're assuming here that the ambient geometry is the Euclidean plane. That's where everything happens, right?
Euclidean space,
yeah.
RD.
Okay, thanks.
There should be no big issues for a Riemannian manifold.
I mean...
Okay, let's take RD for the moment. Okay, so the list of concrete problems is over. Now we can just for say 10 minutes forget about it and have our overview on currents instead. And then we'll try to put the two things together. So what are currents? Currents have been introduced by the RAM and then borrowed in geometric measure theory to tackle the plateau problem with direct methods. What's the plateau problem? You are given a boundary, say we are in R3, we are given a closed curve, and we are looking for the minimal area, so the smallest surface spanning that boundary. This is the plateau problem, and if you want to run a direct method, what you have the two main ingredients you need is compactness and lower semi-continuity of the functional. Here the functional is the area, so you have the lower semi-continuity, but you don't have any compactness in the class of smooth surfaces. So what we do instead is to enlarge, crazily enlarge the class of surfaces and introduce currents. I have to be honest, currents can be scary, but in our case, it suffices to consider zero-dimensional and one-dimensional currents. So we'll see they're pretty easy to deal with. So by definition, a k-dimensional current, T, is a functional. So it acts on tests, is a linear and continuous functional on the space of smooth k-dimensional forms with compact support endowed with a suitable topology. And the current always comes with two objects which are fundamental for the plateau problem, the boundary and the mass, because in the plateau problem you want to prescribe the boundary and minimize the mass. The boundary of T is, well, consistently with our intuition, a k-1 dimensional current, so it's one dimension less. And it's defined in this way. So you take a k-1 dimensional smooth form, alpha, and the evaluation of the boundary of the current on that alpha is defined to be the action of the original current T on the exterior derivative of alpha. So if alpha was a k-1 dimensional form, its exterior derivative is a k-dimensional form. As for the mass, you just take the operator norm, so the supremum of the action of the current on tests with cone mass less than 1. So just to have some simple cases. When k is equal to 0, well, you can recognize the very definition of a distribution. It's really that one. And this is good news on one side, because we know distributions. But it's also bad news, because distributions can be really ugly and messy. And what we're saying is that distributions are just one tiny little specific subcase of currents. So our class is really huge. What I usually say is that you have to imagine a current like a distribution which carries a richer geometrical structure. The other simple case is really simple, meaning that currents have been introduced to generalize surfaces. So well, if you start with a genuine smooth k-dimensional surface, you have a canonical way to associate a current to this surface. And it's the obvious way. So the action of the current associated with the surface on a k-form is just the integral of this k-form on the surface itself. And you see, with this association, with this definition, you recover the usual notions of area volume, which matches the mass, and the usual notion of boundary. In particular, so the mass of the current associated with the surface coincides with the area of the surface, and the boundary of the current associated with the surface coincides with the current associated with the boundary of the surface. Okay, why are we so happy about currents? Well, because we can run the direct method. But as I was saying, currents, I mean, generic currents are crazy objects. So now we have to shrink our focus, our set, to a smaller class of currents which still resemble surfaces. And it is the class of integral currents. An integral current is a current with finite mass, boundary with finite mass, and a representation which should remember this expression we've seen here. Because you see, the action of the current can be written as an integral on a k-dimensional rectifiable set of this integrand, which is the pairing of the test with the orientation of the rectifiable set, which exists almost everywhere for the rectifiability. And then we multiply it by an integer number, because this theta is an L1 function with coefficient with values in Z. So you have to think to this theta as really the folding number of your surface. Okay, and the good news is that with this definition, we still have the compactness we need. And this is a celebrated theorem by Federer and Fleming, saying that the class of integral currents is closed. And as a corollary, you can solve in a standard way your plateau problem. In particular, if you're given a k-1 dimensional submanifold, there exists a mass minimizing integral current with that boundary. So now we have like a black box, a standard way to treat the plateau problem. In our case, it is even simpler, because our plateau problem has a 0-dimensional boundary and a 1-dimensional surface, which is something easier. And there is this theorem I like to mention, even if its importance is not like the one of Federer-Fleming's theorem, because this theorem tells you that one-dimensional integral currents are really the object we need. So a one-dimensional integral current is always decomposable. It means that you can split it in the union of countably many Lipschitz loops and finitely many Lipschitz curves. So a finite number of open curves and some loops that we will rule out very quickly, because of course they will be increasing our energy and we want to minimize it. Okay. Now just some quick word about calibrations. What is a calibration? Which is a tool that we'd like to use. A calibration is a K-form which comes automatically associated with a K-dimensional current. This K-form fulfills some assumptions. You can see the list here. So whenever you couple it with the tangent to the rectifiable set, which is the support of the current, it gives you 1. It is closed and it has commas less than 1. But the important thing about the calibration is that its mere existence is a sufficient condition for the associated current to be a mass minimizer for its own boundary. So here you can see the result I've just said, and also the proof. I've put it here because it's just one line. So what is important about calibrations is that if you're able to build a calibration, you do not need anything else. That is a sufficient condition to say we're looking at a minimizer. Okay, so now we want to put the two things together. So try to treat our network problems, minimal network problems, with currents. So it's obvious that an oriented graph with multiplicity is a polyhedral integral current. And what's the motivation? Why are we going to do that? Because if we treat the optimization problem as a plateau problem for one-dimensional currents, we will have the black box I was saying before, so a solid existence regularity theory. And then calibrations as a shortcut for computation in some cases. And then other geometric measure theory techniques like polyhedral approximation, blow-ups, and so on. Okay, these are the dreams, say. Now, what do we need to set a plateau problem which matches, which imitates the network problem? Well, first of all, we need to establish what is our boundary. So we need a boundary for currents, a zero-dimensional current, which is a boundary and matches source and sinks, that mu plus and mu minus in the problem. And I'll tell you in a moment what I mean with the Kirchhoff's law. And then we need a mass which matches the energy. So the plateau problem means minimizing the mass. In the network, in the optimal network problem, we want to minimize the energy. Now we need to pair the two things together. So let me explain the main difficulties with a picture. So let's start with the Steiner tree problem, which is somehow our worst case scenario. And let's start with very easy cases. For instance, imagine we want to solve the Steiner tree problem with the vertices, the 4 vertices of a square in R2. So we already know the solution is this one. And also the rotated one, this one, where the angles at Steiner points are, even it doesn't seem so, 120 degrees. So what can we do with currents? Well, let's start with a boundary. So we need to put coefficients on the 4 points at the vertices. And we try to do the simplest thing. For some reason, we get that the sum of the coefficients should be 0. Otherwise, we would creating some hidden boundary inside. Okay, so we start with 1 minus 1, 1 minus 1. Well, this is not the right choice, because if we minimize the mass of the current with this boundary, if we solve the plateau problem, what we get is 2 segments. So not only this is not the solution we wanted to see, this solution, the support of this solution is not even connected. Okay, let's go on with the problems. So for instance, let's see if we can obtain something better from a simpler example, the vertices of an equilateral triangle. So again, we know what the solution should be, and this should be a segment. I'm sorry. Okay. This is what we want to see. Start with the coefficients. Well, here you see, if you want to respect the Kirchhoff law, you want to have precisely this boundary, you have to have coefficients with a sum which is 0 and break the symmetry of the equilateral triangle. So for instance, you put 1 here, and -2 in here. And what happens is that the mass minimizing current with this boundary, unfortunately, it is this one. Why? Because if you compute the current with this support and these coefficients in the boundary, what you see is that here you have multiplicity 1, here you have multiplicity 1, here you have multiplicity 2. So you count this segment twice. While in the Steiner tree problem, you want to count the length of this segment just once. Because as we were saying, it doesn't matter how many particles you send through this segment. The only thing that matters is that you built that piece of pipe. Okay, so now we are ready to move in the framework of currents with coefficients in a different group, in a group which is not anymore Z. And let's try to figure out which are the assumptions we have to make on this normed group, so a group with a norm. We have 3 coefficients, E1, E2, E3. The network will be something like that. So here we will have multiplicity E1, E2, and here it is E1 plus E2. Well, and which are the requirements? First of all, Kirchhoff's law. So E1 plus E2 plus E3 should be equal to 0. Or if you prefer, E3 should be equal to minus E1 plus E2. Okay, and this is to respect the boundary. And then, to enforce connectedness of the set, you see, the real trick is to treat the standard tree problem like an irrigation problem. Break the symmetry and decide that there is one arbitrary point that is your well. In this case is the right point. Okay, in terms of the group, this means that whenever I take a subsum of these 3 coefficients, so I take E1 plus E2 or E2 plus E3, E1 plus E3, I don't get 0. So it's a linear independence. So in this simple case with 3 coefficients, it is enough to require that they are different from each other. And then the last thing, to have a mass which matches the cost, which is just the length of the set, in this case of the standard tree problem, well, the norm should be 1 for E1, for E2, and E3. So I between 1 and 3. Okay, this is more or less what we need. Now we go back to the presentation. And we decided that we need currents with coefficients in groups. So you start browsing the literature and you discover that they actually exist. They were introduced by Wendell Fleming in the 60s. And then there is a whole literature developing that definition of what he called flat chains over a finite coefficient group. But the theory by Fleming was not suitable for us because he obtained this kind of currents through a closure procedure. So he took k-dimensional polyhedral currents with coefficients in a group, and then he took the closure with respect to the flat norm, with respect to a suitable norm. What we need instead, for our purposes, calibrations and things like that, is an integral representation, the one we had for integral currents. So we really need to write down the integral on the rectifiable set of this and that, and we see the coefficient. And because when we compute the mass, in this case, we have that the mass is the integral on that rectifiable set of the norm of the coefficient. And this is really what we need. So we developed a parallel theory. Of course, they are compatible. And we start from the functional analytical definition of currents that I showed you in the overview of currents. So we consider Rm as the space of coefficients. So the ambient space is still Rd, but the coefficients are in Rm, which is endowed with a norm. So you see that the space of one-dimensional currents was defined in duality with a space of smooth one-dimensional forms. Now our space of one-dimensional currents with coefficients in Rm is built in duality with one-dimensional smooth forms with values in Rm. In this way, we can still give a definition of integral currents with coefficients in Zm, and the representation, well, it looks pretty much identical to the one I showed you with the definition of integral current, with coefficients in Z. There is just one tiny little detail, which is this dot in here. So this time, we are taking the integral on the rectifiable set, the support of the current, of the pairing between the test form and the orientation, which is this time a vector in Rm. So this is a vector. This is a vector in Zm, and then we're taking the scalar product of the two. So we get a real number, a scalar number, as an integrand, and we can perform the integral. So you see, this time the coefficient theta is a function with values in Zm. And for polyhedral currents with coefficients in Zm, what we see is the naive representation we gave at the beginning of the seminar. So we still have the sum, it is not a formal sum anymore, of segments. And then here we have the orientation of the segment, this tau I, which is constant along the segment. Rank 1 product with the multiplicity, which is this vector theta I. Okay, what about the choice of the group? To apply the theorem of currents with coefficients in group that we just introduced, we have one first requirement. Our discrete normed group should be a subgroup of a vector space, Rm, in our case, for some m. And then to treat an irrigation problem which has m+1 boundary points, we are going to put m+1 coefficients, so u1, em, em+1 in G, such that, and these are the properties I listed before, the sum of the m+1 coefficients gives 0. This is the Kirchhoff's law. Every subsum is different from 0. This is to guarantee connectedness of the solution. And then at last, whenever we take the sum of k different elements at k different coefficients, and then we take the norm, what we recover is the cost at k, the cost matching. Okay, with this procedure, we obtain our first theorem, which is an equivalence theorem between the Eulerian formulation of the branched optimal transport and the solution of the plateau problem for currents with coefficients in a suitable group. So let me rephrase it. We start from mu minus mu plus to atomic measures, and we have a canonical way to build from this boundary datum a group depending only on the number of points involved in the two measures, and a norm on the group depending on the cost, in such a way that the energy optimization for the branched optimal transport problem is equivalent to a mass minimization problem, so to a plateau problem for currents with coefficient in that norm group. In particular, if the cost is the usual power alpha of the branched optimal transport, the irrigation problem can be solved in z to the power n with a norm which is L to the power 1 over alpha. Now I'm showing you the reason why this is true. And the standard tree problem on n+1 points can be solved as an irrigation problem in Zn with the L infinity norm.
I wanted to ask several questions here. So first of all, these measures, they're positive measures here. They're not something.
Yes, absolutely, positive measures.
So and G, so when you say norm group, so you still mean an abelian group, or what sort of group?
Yeah, it's abelian. In our case, actually, it turns out to be just the lattice.
So it's a finally, it's actually Z to the n with some sort of a norm, yeah. Right? I see. Okay.
Yeah, in these specific cases, it's just the lattice.
Okay, thank you.
You're welcome. So let me show you which groups and norms we're building. So let's still think about the Steiner tree problem. So we were saying that we want to solve the problem. We have 3 points. So our group will be the lattice Z2 in R2. And we take as E1 really the 1, 0. So this is E1. E2, it is this one. And then we have to choose the norm in such a way that each EI has norm 0. So this vector has norm 0, this vector has norm 0, and their sum, which is more or less in here, E3, the opposite of their sum, has norm 0, norm 1. Sorry. So the norm, which does this, the unit ball of the norm doing that is the square. So really the unit ball of the L infinity norm. Giving norm 1 to E1, E2, and E3. This for the Steiner problem. What about a branched optimal transport for alpha equal to 1/2, for instance? Well, imagine you have the vertices of a triangle. Well, I should have said it. In this case, it is well known that the angle here is 90 degrees. You still have E1, E2, E3. This is E1 plus E2. And this time you solve the problem in the lattice Z2 in R2. Okay. With which norm? Well, again, E1 has norm E1, E2 has norm E2, but this time the norm of E1 plus E2 should be square root of 2, right? So if this is minus E1 plus E2, that is E3, this should have norm square root of 2, which means that the unit ball is the Euclidean unit ball, the circle. This is because we chose alpha equal to 1/2. Okay, so we have this canonical way to associate the two problems. Why is this approach useful? First of all, because we can find calibrations. And calibration, having a calibration this time means, of course, that we do not have a full solution to an NP problem. But it means that in some special cases, when we strongly suspect that something is a Steiner tree solution, we can try to look for calibrations. Because as soon as we have a calibration, we have like a certificate of minimality, and we do not have to do those heavy computations anymore. So we exhibited some of these calibrations in the paper with Andrea Marchese, and then we proposed an algorithm in a joint paper with Eduardo De and Boshi Belisco. And then we can also find calibration for branched optimal transport, so for any of these power alpha, and also give some exotic counterexample. Okay, what about the multi-material transport problem? So the broadband over power line communication technology problem. Well, I'm running out of time, so I'll try to be as fast as I can. What about the discrete multi-material problem? You remember, in that case, we needed currents with coefficients in Zn, even at the beginning, to give a Eulerian formulation of the problem, because in that case, the multiplicity was already a vector with m entries. And in that case, we had a cost which was defined in Zm. So the cost should fulfill some reasonable assumption. It has to be even, increasing, of course, subadditive, because otherwise we don't have this branching effect. And what we proved together with Andrea and Riccardo Tione is that even in this case, we have the existence of an energy minimizing one-dimensional current with coefficients in Zm. The interesting thing about this theorem is not only, okay, its content, the fact that we have the existence for a minimizer. But also the fact that actually we do not prove this theorem. We obtain it as the corollary of the plateau problem theorem once we convert this problem, this energy minimization problem, into a mass minimization problem. So what is the convexification? You remember the Eulerian formulation meant having a sum of segments and coefficients in Zn. And then we had an energy which was computed as the length and the cost evaluated at the multiplicity. Replacing Zm with Zn, where n is way bigger than m, with a norm, which depends on the cost, we can replace the original current T with a T tilde, which has coefficients in Zn. And this time, instead of computing the energy, we can compute the mass of the current, coinciding with the energy. So in this way, we can exploit the plateau problem solution. And this is the content of the theorem you're seeing here. So there is an equivalence between the Eulerian formulation of the multi-material transport problem with cost C and the mass minimization problem of currents with coefficients in Zn. Why is this approach useful? Well, again, because this is the way we prove existence for the energy minimizer in the multi-material transport. So we can, again, borrow techniques from geometric measure theory. And well, I've started with a concrete example, so let me also finish with a concrete example. This is the only way we know to treat the oriented mailing problem. What's the oriented mailing problem? Well, it's pretty much the opposite of the optimal transport. In the optimal transport, we said that if you have discrete measures mu minus and mu plus, it is just a problem of combinatorics, of reshuffling the points. In the oriented mailing problem, this coupling of which particle goes where is already done in the data, in the datum of the problem. So we're, well, the name says it. We're really saying someone is writing the letter and someone should receive the letters. Someone precisely located in a point on the space. Or in pre-COVID time, you would say someone is living at home and goes to work in some precise place. Well, for the oriented mailing problem, the only way we see to treat the problem, to optimize the problem, is to treat it like a multi-material transport problem. So to register in the traveling particle on the network, not only who's the sender of the letter, but also the direction of the letter in such a way that you avoid cancellation between letters traveling on the same segment, but in two different directions. Okay, with that, I conclude. I thank you for your attention.
All right, thank you very much. Let us thank Annalisa.
Thank you.
Thank you. Okay, so now the floor is open for questions. So if you have any questions for the speaker, you are welcome to ask them. So I actually have some questions. So let me try to remember. One question concerned ambient geometries. So whether you thought about how different things would be, let's say, in a hyperbolic space, you know, as opposed to RD, you know, because I think that a related question is what happens if instead of trying to solve this plateau problem precisely, you want to solve it approximately with a small error, because I think that in the Euclidean plane, finding the Steiner tree precisely is probably somewhat hard, but in the hyperbolic plane or hyperbolic metric space, finding the Steiner trees approximately should be relatively easy. You know, and from the complexity point of view, if one only wanted to find approximate solutions, that probably should make a substantial difference. I don't know how it affects, you know, all this business that you are trying to describe, you know, so I have very little feeling about this. But my feeling is that at least if one thinks about these questions sort of not as sort of on the nose questions, but as approximate problems, then the ambient geometry probably should start to matter. So
yeah, if I understand correctly, you mean the hyperbolic space because you're forcing certain directions to be taken. It's like having a roadmap already written. In
yeah, so somehow
space.
the Steiner trees, the minimal networks in the hyperbolic space or in delta hyperbolic metric spaces, they look different than, I mean, they're easier to find. And I mean, I haven't thought about complexity issues very hard, but my impression is, you know, imagine that if your ambient space is a tree already, right? You know, so this extreme situation, then it's easy to find. It's easier to find minimal networks, right? Even and it's easier to find an actual Steiner tree, you know. So, and a hyperbolic space is to some extent an object like that. And if you are willing to live with some small errors, then you know, you can do something. So at least this is my sort of feeling about this business. I don't know. I'm sort of a complete outsider, you know. So, but I think that if one wanted to find minimal networks precisely, then it's probably still hard. Even in an object like a hyperbolic plane, you still need to do some kind of fine geometry. But if one wanted willing to live with some relatively small errors in relation to cost, then it probably becomes easier. So there is a comment from Sasha saying that it is hard. I'm not sure what.
Wait.
Anyway, you know, so that's sort of question, comment, both, you know, something that I had about this.
So I have to confess that we didn't think about the problem of the ambient space from the point of view of softening the complexity of the computation for the Steiner trees, for instance. But we thought about other ambient manifolds for the problem in general. And, you know, for the plateau problem for currents is not really that different. For our problem, we couldn't spot anything different, at least in the part of theory that I told you today. But we found a pretty curious counterexample for this kind of problem. So let me draw a little bit. Maybe I can explain better what I mean. Okay, the problem is the following. As long as you have discrete measures, so you have these oriented graphs with coefficients in Z, you don't really have big problems, big issues. The problem becomes more sophisticated when the measure is diffuse. In that case, one partial result you're interested in is the following, we called it the homogeneity problem, which is the following. You have, let's start with the example that works. You have your points and you want to solve a sort of Steiner problem, right? Usually you have 1, 1, minus 2, yeah. And your network, minimal network, is this one with coefficients 1, 1, and 2, which is counted once. Okay, what if you double the coefficients? So you have 2 particles in here, 2 particles in here, and minus 4 in here. Well, for the Steiner tree problem in the Euclidean setting, the minimizer is still 2 copies of the minimal network with multiplicity 2, 2, and 4 in here. We had this ugly counterexample. I don't remember the numbers correctly, but imagine you live in an ambient space where only these paths are allowed. Okay?
Yeah.
And you want to send 2 particles living in these lower points above. When you do that with just 1 copy of the problem, you send this particle on the left side and this other particle on the right side. Okay, when you double the boundary datum, so here you have 2 minus 4, the solution is not anymore 2 copies of this lateral roads, say, but this plus this one. So there is one particle traveling along the blue path and the other particle traveling along the red path. And one particle in here traveling along the blue path and another particle traveling here. If you choose correctly the lengths, the distances of these points, you get an actual counterexample. And this means that this lack of homogeneity means that you cannot anymore think to pass from the discrete problem to the diffuse problem with a process of just taking portions of the particles, because something different is happening when you're taking multiples. Mm-hmm. And this was actually quite scary for us. So this was an effect true only in a different manifold, not even a manifold, a gamma limit manifold, I mean, with just these rods.
Okay. All right, very good. Are there any other questions to the speaker? Okay, if not, let us thank Annalisa again. Thank you very much.
Thank you.
Thank you. So at this point, let me stop the recording.